Today we're going to solve exponential and logarithmic equations. The property of equality for exponential functions is if b is a positive real number other than 1, then b to the x equals b to the y, if and only if x equals y. For example, if 3 to the x equals 3 to the 5, then x equals 5. And conversely, if x equals 5, then 3 to the x equals 3 to the 5. So if the entire left side of the equation has the same base as the entire right side of the equation, then the exponents will be equivalent and you no longer have exponents. And then you can solve for x. 100 and 1 over 10 can be rewritten with a base of 10. 100 would be 10 squared. 1 over 10 would be 10 to the negative 1. On both sides you have a power to a power, so we'll multiply. And now that we have the same base of 10, the exponents are equivalent. So 2x is equal to negative x plus 3. Continue solving. So x equals 1. Let's check. So x equals 1 is our answer. For part B, we would try to find a way to make 2 the same base as 7. But 2 and 7 cannot be made to have the same base. So some exponential functions can be solved by just rewriting the bases of the exponents to make sure they're equal. But if your bases cannot be rewritten to be made equal, then you will need to use the inverse operation of an exponential to solve this. The inverse operation of an exponential is a logarithm. So I'm going to take the log of both sides. And I specifically need to take log base 2 of both sides because 2 is the base of the exponent that I am trying to bring down. Keep in mind that log is an operator. You have to have it in front of whatever you're taking the log of. So if you wrote log base 2 after the 7, trying to mean log base 2 of 7, that would be counted incorrect. That is not correct notation. And mathematically, this does not mean anything. Now that my bases match, I can bring down the exponent based on inverse properties of logs and exponentials. On the right side, I still have log base 2 of 7 because there's no way to simplify that except with a calculator. Let's check. Using inverse properties of logs and exponentials, you indeed get 7 equals 7. So log base 2 of 7 is our answer. This gives us two ways to solve exponential equations. One, where you can rewrite the base, and if you can't rewrite the base, then you'll need to use log. The property of equality for logarithmic functions. If b, x, and y are positive real numbers with b not equal to 1, then log base b of x is equal to log base b of y if and only if x equals y. For example, if log base 2 of x equals log base 2 of 7, then x equals 7. And conversely, if x equals 7, then log base 2 of x equals log base 2 of 7. That makes our first example pretty easy. Here you have ln, which is log base e, of the entire left side of the equation. And then you have ln of x plus 5 on the entire right side of the equation. Now that the whole left side is in one natural log, and the whole right side is in one natural log, we can use the property of equality for logarithmic functions, stating that if the logs are equal, then the arguments are equal. That is also doing the same thing as raising both sides of the equation to an exponent with the base of e, because exponentiating a log and choosing the base of that exponent equal to the log will undo the log and the exponent and leave you with simply the arguments of the logs. Now solve for x. And let's check. That is correct, so x equals 4. For part B, we have log base 2 of the left side, but we have no log base 2 of the right side. Now that we've isolated the logs on either side of the equation, meaning there's not a log plus a log on the left side, the entire left side is log base 2 of an argument. Then we can use the inverse operation of log base 2 to remove the operation of log from this argument. So what do? Exponentiate both sides of the equation with a base of 2. On the left side, because the base of the exponent and the base of the log match, the argument of your log is no longer in an exponent, and you have 5x minus 17 equals 2 cubed. Oh, 2 cubed is 8. Solve for x. Now let's check. Remember, log base 2 of 8 is 3 because 2 to the 3 is 8. So x equals 5 is our answer. For part C, you do not have log of the entire side of the equation. You have 2 logs on the left side. Fortunately, both these logs have the same base. These are the common logs, so the base is 10. Because they have the same base, we can condense the left side of the equation to be written with a single logarithm. You have to condense before you can use the inverse operation of a log, which is exponentiating both sides. So if I have log of 2x plus log of x minus 5, the sum of 2 logs is the same as log of the product of those arguments. Now the entire left side has been condensed to a single logarithm. Use the inverse operation of log base 10 to write the log's argument without the log. We do that by exponentiating both sides of the equation with a base of 10. Now that your bases match, using inverse properties of exponentials and logarithms, the argument of the log is now the left side of the equation. Here you have a quadratic, so bring everything to one side and try factoring. First, let's take out the GCF of 2. 5 times 10 is 50, and positive 5 minus 10 is negative 5. After using zero product property, we have 2 answers, negative 5 and 10. Let's check. Uh-oh, you're not allowed to take the log of a negative. It's undefined. So because log of negative 10 is undefined, negative 5 is not a solution for our logarithmic equation. It is extraneous. Now, I don't know log base 10 of 20 or log base 10 of 5, but I can condense these logs using the properties of logarithms. This is saying log of 100 is 2, and that's true because the base 10 to the power of 2 is 100. So x equals 10 is our only solution. Remember, x equals negative 5 was not a solution, not because it's negative, but because when it was plugged into the original equation, it made the argument of a log negative, and you cannot take the log of a negative.